All right, let's continue on. In the video for example 3.4, we saw how to use a t-test to test the null hypothesis that a single slope coefficient in a multiple regression model is equal to 0. In this video, we continue looking at this question, but we use a different procedure for performing the test, a procedure called the extra sum of squares method. The extra sum of squares method is extremely useful because it not only allows us to easily test hypotheses about a single regression slope coefficient, like we're doing in this example, but it also allows us to test more complicated hypotheses involving two or more slope coefficients. In this video, we'll use SAS Analytics Pro, and I will show you how to implement the extra sum of squares method using ProcIML, the interactive matrix language, as well as the reg procedure. So let's jump in. All right, let's look at example 3.5, the delivery time data set. In example 3.4, we use the t-test to test whether there is sufficient evidence in the data to conclude that beta 2 is different than 0. That is, the null hypothesis is that beta 2 is equal to 0, as shown here, and this is given that x1 is in the model against the alternative hypothesis that beta 2 is not equal to 0. In this example, we're going to use the extra sum of squares method to test the same hypotheses. Now, the idea behind the extra sum of squares method is that we fit two models. The first model is called the full model. All right, that model imposes no constraints. And so in our case, that would be the multiple regression model that contains both x1 and x2. We then fit what is called the reduced model. The reduced model imposes the restrictions or constraints that are given in the null hypothesis. Now, in the null hypothesis here, beta 2 is equal to 0. And if that's the case, then x2 is not linearly related to y. And so we would just leave x2 out of the model. And so that reduced model would be a regression model that just contains x1 as the only explanatory variable. Now, once we have the full model and the reduced model, we get the sum of squares regression from each of those two models. So the sum of squares regression for the full model and the sum of squares regression for the reduced model. We then take the difference between those sums of squares regression, the sum of squares regression for the full model minus the sum of squares regression for the reduced model. And then we divide that difference by the number of degrees of freedom associated with the test, which in this case is going to be 1 because we only have one restriction in the null hypothesis. Now, once we have that, we also obtain the estimate of sigma squared from the full model. And so that would be the mean squared error, or the MSE, from the full model. We then take the ratio of these two quantities to get an F statistic, which we then compare with the upper alpha percentage point of an F distribution with one, in this case, one numerator degree of freedom and denominator degrees of freedom equal to n minus p. And so let's take a look at the Sas code for this. And I'm going to be using two procedures. First, we're going to look at how to do this in ProcIML, the interactive matrix language. All right, and so we are programming this as it's shown in the textbook. And then once we've done that, we'll look at how to do this in ProcReg as well. Now, we have looked at how to estimate the parameters in the multiple regression model, and we've seen how to construct or calculate the values so that we could construct the ANOVA table for the regression. And so we're just going to do that for the full model and for the reduced model. And so we're going to replicate this section that we had up top where we were fitting the model and then computing the quantities for the ANOVA table. And so you can see here, I've got a section called the analysis of the full model, and we're going to estimate the parameters. All right, and we'll calculate these various matrices that are required for that, x prime x here, and then we'll calculate the inverse of x prime x, x prime y, and so forth. And then we calculate the parameter estimates. And then what we did was we calculated the quantities for the ANOVA table. And that allows us to easily calculate the sum of squares regression for the model and the mean squared error. All right, and so you can see here that we first calculate the total sum of squares based on the model or for the response. And then we calculate the sum of squares error for this particular model. And then once we have those two, we can calculate the sum of squares regression by subtraction. Now, notice that I need the sum of squares regression for the full model. I need to save that. And so that's what I'm going to do right here. And I'm just going to call that variable that I'm saving that in SSR underscore full. So we'll keep our eyes out for that later on in the program. I also need to keep track of, count the, or determine that or save the number of degrees of freedom for the full model. And so that's what I'm doing here. I'm going to call that variable dfreg full, right? So I'm just saving that because I'll use that later. And I also need the sum of squares error, the degrees of freedom associated with the mean squared error from the full model. And so I'm going to save that. So I use those values later on. Okay, then we can scroll on down, and we are then going to construct the reduced model and then perform the analysis based on that reduced model. Now, think about what the design matrix looks like. It's got 3 columns. The first column is a column of 1s. The second column corresponds to x1, and then the third column corresponds to x2. And so what I want to do, I want to get rid of that third column. I want to get rid of that third column that corresponds to x2. And the easiest way to do this is to construct a 3x2 matrix. I'm going to call it B here, all right, which has an identity matrix in the first 2 rows, and then the third row is equal to 0. And I'm going to post multiply that matrix against the original design matrix X. All right, but so I don't have to change the labeling of the design matrix in my subsequent code. All right, what I'm going to do is I'm going to save the original X matrix in a variable called xsave, and then I'm going to multiply, post multiply that xsave matrix by this B matrix. Okay, and then I'm going to save that as the design matrix X. And so then I don't have to, I can just copy and paste the code from above down into this section, and it'll calculate the parameter estimates and the quantities for the ANOVA table for the reduced model without having to change anything else. So it's a little bit of a savings there. Now I am going to print out that new design matrix for the reduced model just so that we can see it in the output. And then everything else stays the same here because again, we're just calculating the parameter estimates. Let me see if I can scroll down here, if this thing will behave a little bit. Let's see, there we go. Okay, so we estimate the model parameters and so forth. And so we, again, using the reduced design matrix, we calculate x prime x, the inverse of x prime x. We calculate x prime y, again, using the reduced matrix. And then we calculate the parameter estimates. All right, so continuing on. Well, by the way, I also need to show you that, again, I'm saving the sum of squares regression from the reduced model. And so I will call that sum of squares regression SSR underscore red. We also need to save the degrees of freedom associated with the model for the reduced model. So I'm going to save that in a variable called df underscore reg underscore red. And then I need to, well, I guess I'm not going to use it. I do save the mean square for the reduced model, but I'm not going to, I don't think I'm going to use that down here. So let's take a look. All right, so once we have these quantities saved, okay, then I have this new section, this additional section. This is where we're going to perform the test based on the extra sum of squares method. All right, and so the first thing I'm going to do is I'm going to calculate the difference in the model sum of squares. So the sum of squares regression for the full model minus the sum of squares regression for the reduced model. And I'll save that in a variable called SSR_diff. Then I'm going to calculate the number of degrees of freedom associated with this test. And that's just the number of degrees of freedom associated with the model for the full model, minus the number of degrees of freedom associated with the reduced model. And I'll save the difference in degrees of freedom in df_test, because this is the number of degrees of freedom associated with this particular test that we're performing. Okay, and then we continue on down here. Once we have those quantities, then we can calculate the F statistic for the test. The numerator for this F statistic is equal to the difference in the regression sum of squares for the two models divided by the degrees of freedom for the test. The denominator is the mean squared error from the full model. Now I'm applying a format attribute to the F statistic so that we can see lots of decimal places. And then once we do that, we calculate the p-value, as we've seen in at least one other previous lecture video. And again, the number of degrees of freedom for the test are going to be equal to df_test. That's the difference in the model degrees of freedom for the two models, the full model minus the reduced model. And then the denominator degrees of freedom is going to be associated with the degrees of freedom for error for the full model. All right, so that's really all there is to it. You can see here that what we're doing is just fitting two models, the full model and the reduced model. The reduced model imposes the restriction that is stated in the null hypothesis. We get the appropriate quantities from the ANOVA tables for the two models, the sums of squares regression for the two models, and then the degrees of freedom and so forth. And then we just apply this calculation. And so let's see what we get here when we run this. And I just scroll up here. Okay, there's the original data set. I just want to show you that, because now if we go down to the section for the reduced model, the analysis of the reduced model, notice that by post multiplying it by that what I called the B matrix, okay, we got rid of that third column in the X matrix. And so now I'm just applying that same set of code to calculate the parameter estimates. Okay, here we have beta 0 hat and beta 1 hat for the reduced model, and all the other quantities that go along with the ANOVA table for that. And now here we have the section perform the test using the extra sum of squares method. And so I printed out the quantities that I saved and used down in this section. So we see here that the sum of squares regression for the full model was 5550, 0.8109. The sum of squares regression for the reduced model was 5382, 0.4088. The difference is 168.40213. The degrees of freedom associated with this test is equal to 2 minus 1, which obviously is 1. All right. And then the error degrees of freedom for this test would be 22. And then finally, you'll recall that the mean squared error for the full model was 10.624. All right. And so what we do then is we take this difference, the sum of squares, the difference in the sum of squares regressions, divide by the degrees of freedom for the test, and then we divide that result by the mean squared error for the full model, and we get the F statistic, which in this case is 15.851 approximately. And then the p-value for this test is 6.312 times 10 to the negative fourth. So that's fairly small. And so we can see that there's strong evidence against the null hypothesis that beta 2 is equal to 0, given that x1 is in the model. And if you happen to take notes, or maybe you remember the p-value that we got when we used the t-test to test this same hypothesis, you'll recall that you'll notice that we're getting the same exact value. So these are equivalent tests. All right, now let's look at how to do this in proc-reg. All right, and so again, the idea is that we fit two models. We fit a full model and we fit a reduced model. Now that's very easy to do with proc-reg. Here, let me show you. Okay, so here we have the full model. All right, and you'll notice that I've got both x1 and x2 in the model. So that's the full model. And then I fit the reduced model down here below it. And all I've got to do is just, include x1. I just, not include x2. And so that's my reduced model. Now, I am also, let's get rid of that for now. We don't need that. And so then once we run those two procedures, we're going to be able to get the values that we need to perform this calculation. So let's run this. And I'm going to go ahead, I'm going to select this portion of the code. All right. And so let's go ahead and run that. Okay. And so you can see here, we get the results for the full model. All right. And we also have the results for the reduced model. Now, what do we need? Well, we need the sum of squares for the model, for the full model. So the 5550.81092. We also need to keep track of the degrees of freedom associated with that model. We'll also need to save the mean squared error for the full model. From the reduced model, we need the model sum of squares. We need the model degrees of freedom. All right. And then what I'm going to do, and nothing fancy here, I'm just going to copy and paste those quantities into this data step. So I'm creating a data step or a data set called test, and I'm copying and pasting in the quantities from the ANOVA tables for the two models, the full model and the reduced model. All right, and so you can see here that I'm this code basically mirrors the portion of the code in the proc-IML program that was at the bottom after we had fit those two models. All right, so let's take a look. Let me just say that this is, this is pretty basic, copying and pasting these quantities from the output into this SAS program. It's possible to get those values programmatically, but it's a bit cumbersome, to be honest with you. And for a simple example like this, and for time purposes, it's really perhaps not worth it to do that. All right, and there's another reason why it really is unnecessary that I'll show you in just a second. But this is, this is how we can implement that extra sum of squares method in the context of using proc-reg. So let me go ahead and run this section of code. Okay, and you see here the output from that section. And so we see here we've got the sum of squares regression for the full model, the sum of squares regression for the reduced model, the difference in the sums of squares. We see the number of model degrees of freedom for the full model, the number of model degrees of freedom for the reduced model. The difference is the number of degrees of freedom associated with this test. We saved the MSE from the full model. And then we calculate the F statistic, which is 15.8508. So that's exactly what we got using proc-IML. And the p-value is 0.000631248. And that's what we got when we used proc-IML. So we get the same exact result, as should be the case. And so this is how you can do this using proc-reg. It's as simple as fitting a full model, all right, right here, and a reduced model right there. But now let me show you one more way to actually perform this test, right? And again, this is the test that we're talking about. We've seen how to do this test using a t-test. We've seen how to perform this test using the extra sum of squares method. All right, but there's a much easier, more straightforward way, and that is just to obtain the same result from the parameter estimates table in proc-reg. And so what I'm going to do here is I'm going to run proc-reg, just a single model. I don't have, it's the full model, right? I don't have to bother with fitting that reduced model. But as part of my output, I want to see the parameter estimates table that proc-reg produces. All right, and so let me go ahead and run this portion of the code. All right, and so you can see here that this is what we get. And in fact, let me do this. I'm going to, I really don't even need the ANOVA table. So I'm going to rerun that just to kind of clean things up. And this is what I'll post. All right, so here we have the parameter estimates table. I want you to look at this line for the x2 variable. And you can see here that we have a t-value and a p-value. Now, if you square that t-value, you're going to get the same value as this F statistic up here. All right, you're going to get 15.85. And notice that the p-value, which is listed here, it's rounded to 4 decimal places, 0.0006. It's the same as this p-value up here that we got using the extra sum of squares principle in proc-reg. And so the bottom line is that the tests that are being performed by the t-test, by the extra sum of squares principle, it's the same exact test that SAS is providing for us as part of this parameter estimates table. All right, and so anytime you do a regression and you look at the parameter estimates, the t-value and the p-value are testing hypotheses exactly like this. All right, they are testing the null hypothesis that particular that the slope coefficient for that particular variable is 0, given that all of the other variables are in the model, against the alternative hypothesis that slope coefficient is not 0. So that's how you can implement and perform the extra sum of squares method using proc-reg, proc-IML, but again, in a much more straightforward way, just using proc-reg and looking at the parameter estimates table. So now you know what hypotheses are being tested in that parameter estimates table. All right, and so, whenever you're using a statistical package, whether it's SAS or R or Stata or, any other package, there are typically going to be lots of p-values that are produced by the software and that show up in the output. And you need to know what those p-values represent, what hypotheses are being tested. And so now you know what these p-values are testing in this parameter estimates table in SAS proc-reg. But what if we want to test more complicated hypotheses than something as simple as a slope coefficient being equal to 0, given that all the other variables are in the model? Well, that's where the extra sum of squares method really is very, very powerful, because again, it allows us to test hypotheses that are more general, that are more complicated than this, and for example, that involve more than one slope coefficient from the model. And so we're going to look at yet another way to perform this kind of a test using proc-reg that implements something that is at least equivalent to the extra sum of squares method, but it's much easier to carry out than trying to program our own in proc-IML. But we're going to see that in a different lecture video. So I'll see you at that point.